Hi, this is Toby Howard from the Department of Computer Science. I'm going to be teaching the Understanding Databases course unit in September. And this is a very short presentation to look at some of the basic ideas of algorithms that I think it would be useful for you to know about. We're not going to go into a great amount of detail. There's lots of references out there if you want to look at things further. But there's some ideas here that I think will form a good basis for what you're going to do in the databases course, and perhaps some of the other courses too. So I think we probably already know what an algorithm is, but it's worth saying, so we're all on the same page. It's a step-by-step recipe or method for solving a problem. Some algorithms are simple, some are medium, some are quite difficult to understand. So there's quite a range of stuff going on. We're going to start with a simple one. These are my favourite noodles, and I eat them whenever I get the opportunity. They're instant noodles, and you have to follow a specific set of operations when you want to make them. And here we've got them arranged left to right, top to bottom. And if you don't follow them in the right order and obey the instructions properly, your noodles may not turn out very nice. And in fact, last year, I wasn't paying attention when I was making the noodles. I was thinking about something else. I did things in the wrong order, and they came out horrible. So following things in the right steps is very important, especially when it comes to doing things with a computer. So let's look at algorithms in computer science, which are generally more complicated than making instant noodles. Here are some examples of some very common types of algorithms. These crop up again and again throughout computer science, across all aspects of computer science, and they crop up in different ways, in different spaces with different applications, but they tend to keep coming up. And let's go through them. Searching, finding data in databases. As you will know, databases are getting bigger and bigger and bigger, and the challenges of finding data, searching for data quickly, are really quite exciting. Sorting data. Once we've found our data, how do we sort it into a helpful order? We could order it by name or date or address or time or size. You get the idea. How do we filter and optimize relationships within the data? How does a route finding app on your phone or your tablet find the most efficient route between A and B, which must take into account factors not just like the topology of the roads or the railway or whatever mode of transport you're using, but the current conditions. Are roads closed? Is the delays to transportation and so on? All this stuff has to go into the algorithm. And finding connections between data in large data sets. A very common application of this is targeting ads at you when you're using the services that we all use. And you will notice that sometimes it gets it right, and an ad will pop up and it's something you're particularly interested in, or something you recently bought on Amazon and you think, oh, I wonder how Facebook knows about that. Or it's something that you're not at all interested in or expecting, and it comes as a surprise. What's happened? The algorithm that has tried to choose the most appropriate ad for you has failed. So all those different types of algorithms, and in all the different ways that they crop up, what do they have in common? I've picked a few things out here, and these are things, sort of real-world constraints that algorithms have. Data's getting bigger and bigger, as we all know. Google doesn't tell you how much data it's got in its data centers around the world, but people estimate it's something at least 1 million gigabytes. That's a million terabytes. But who knows? And algorithms have to work with all this huge amount of data, and they also have to be able to do that quite quickly. And in fact, it's stronger than that, isn't it? It has to be as fast as possible. Google, it's been calculated, gets about 70,000 searches every second, and it's able to return results in usually under a second or about that. Try it out next time you're searching, if you're using Google or any of the other search engines, actually, and see how long the response gets to come back. The algorithms have somehow been able to operate very, very quickly. And if they don't, we'd all give up and go home if we had to wait 10 minutes for every search, or even 5 minutes, or even a minute. We haven't got the patience for that. Another thing all these different types of algorithms have in common is that they have to give correct answers all the time. If an algorithm gives an incorrect answer, shows you an ad that doesn't make any sense to you, it's failed. And failing algorithms can range from the annoying, those ads that you don't like, to the catastrophic, self-driving cars, aircraft control systems, traffic light, embedded systems in traffic light controllers on roads. They all run algorithms. If the algorithms go wrong, that's bad. Algorithms must cope with corrupt and unexpected data because that's what data's like. It goes bad, or strange data comes in when you're not expecting it. If your algorithm can't recognize that the data that it's trying to deal with is not the right sort of data for it, then again, the consequences could be bad. And finally, and perhaps not immediately obvious, is that an algorithm must be understandable. You must be able to write down, document the steps that your algorithm takes and the constraints that it operates under. Otherwise, you can't communicate it to anybody else. You can't continue to develop it. You can't revise it. You can't fix bugs because it's not well understood and it's a big mess and we're in trouble. So let's look for a moment at performance of algorithms. I hope I've given you the feeling that with all this big data, we need to be able to run algorithms over the data quickly. Classic problem for algorithms is how to sort data. Here's a little example of some numbers, a list of numbers, and we want to sort that list so that it's in a numerical order. Not very exciting, not very interesting, you might think, but this kind of sorting, numerical or otherwise, alphabetical or some other type of sorting, it's absolutely everywhere. Every time you open a browser, you're sorting data. If you're looking at your folders on your PC or your Mac or a device, you want it sorted in some way by name or date or size, and you want that sort to happen instantly. You don't want to wait 30 seconds or even 10 seconds. You want the instant sorting. So this is sorting is a hugely important topic, very interesting. It's got a 60-year-old research history back to the early days of computers, and it's still a hot topic of research today, very hot. People are working on it all the time. Data's getting bigger, so our searches need to be faster and faster to cope with that. So here's a list of some of the sorting algorithms that people have developed over the last few decades. I'm not going to go through them all. There's actually lots more than this. You can look them up if you're interested. Some of them have got funny names: bucket sort, comb sort, sleep sort, gnome sort. We're not going to go into all these, obviously, but I'm going to pick out just two: bubble sort and quick sort, which are two of the most widely used and most understood sorting algorithms. Let's look at bubble sort first. What we're seeing here is a load of data, and the algorithm is very simple to describe in words. It's going from the beginning to the end of the list over and over and over again, and as it does so, it compares each pair of data items that it finds. And if one is bigger than the other one, or smaller than the other one, it swaps them around so that they're in ascending order. Let's let it run again. And you can see that it just goes back and forth over the list. And this is called a brute force algorithm because it's just plodding away. There's no attempt to make it clever at all here. It's called bubble because you can see, I hope you can see here, this pair of data points, for example, is bubbling down until it's sorted. That's where it gets its name from. So it's simple, but it's slow. Let's look at a different sort of algorithm. This is too complicated for me to explain now. All we need to say is that it splits the list up into sublists, does a sorting operation on each of the sublists, and then combines them together in a clever, complicated way. And if any of you are familiar with the term recursion, this is a recursive sorting algorithm. But don't worry about the details. And you can see immediately, I think, from the little animation here that the way it operates isn't nearly as straightforward to see as the bubble sort algorithm. Let's let it run again. Okay, so it's swapping things around quite a long way away. It's then splitting into two partitions and operating first on the left-hand side, and then it's splitting that into a smaller partition doing something, and then it's another partition, and you can see it's beginning to look sorted, that half, and then it's repeating the operation on the second half. And we end up with a sorted list. This is a complicated algorithm, but it's much faster than bubble sort. Let's go back to our big list of sorting algorithms is here. The obvious question that we need to ask and I'm sure it's been on your mind already, is which is the best one? A difficult question to answer. Here's a simple visualization of just 4 of them, the 2 that we've just looked at, and I've chosen 2 other ones, selection sort and insertion sort. Details don't matter. The x-axis is the size of the list of things that we're trying to sort, getting bigger and bigger and bigger. The y-axis is how long the sorting operation takes. And you can see bubble sort, as the list gets bigger, the sorting time goes up quite quickly. Selection sort, different algorithm, it goes up, but not as fast. Insertion sort goes up as well. But look at quicksort, very interesting behavior. The performance of quicksort, roughly speaking, doesn't really change with the amount of data that you put into it. Think what that means when you're working with vast amounts of data, millions and millions of gigabytes of data. Very important to choose the right algorithm. So those graphs that we've just looked at were actually made by doing experiments with real programs on real data and having a stopwatch running. Generally speaking, in computer science, we analyze algorithms mathematically, often without running them, just by looking at them and thinking about them and reasoning about them, and increasingly using other programs to reason about them. So we have algorithms reasoning about algorithms. We need to measure the time that the algorithm takes to run as the data size increases. And very important point here is that this has got nothing to do with the speed of the computer that you use. It doesn't really make sense to say my algorithm runs very fast on a huge cloud computing center, which has got lots of things running in parallel. My algorithm's fine. But if I run it on my phone, it doesn't run very quickly. That's not the comparison that we're interested in. We're interested in the algorithm itself, regardless of the platform on which it runs. Similarly, we need to measure how much storage space an algorithm needs for its housekeeping as it runs, its own data structures. And if you look into this a bit further, you'll soon meet something called the big O notation, which I'm not going to talk about here, but if you want to find out more about the way that algorithms behave, this is what you need to look at. And there's a thing in the references later at the end of the slides for you to have a look at. I've mentioned correctness before. Increasingly, people are demanding that algorithms are formally, mathematically proved correct. So that, you can certainly test algorithms' correctness by running them on sample data, but are you always sure that you're going to cover all the possibilities with your sample data? Are you forgetting something, some funny type of data that might come in that you haven't thought about? Your algorithm will fail. So if you can prove your algorithm mathematically correct, you're on much stronger ground. And that comes back to the point I made a few minutes ago, that in order to perform a mathematical analysis on an algorithm, it has to be very clearly described. Otherwise, you have ambiguities and you're moving away from formal correctness. And perhaps the final thing to mention here is that analyzing and thinking about algorithms helps you to create new algorithms. This is TimSort, which is the standard built-in sorting method in modern releases of Python, also in Apple's language Swift, in Google Chrome, the Android platform, and Java. And TimSort, I can't go into the details of how it works beyond saying that it does a pass on the data first to figure out what kind of data, and in particular, whether any bits of the data are already sorted purely by chance, which actually happens quite a lot. You get little pieces, little subsets of the data that are already sorted. So there's no point spending too much time sorting them if you know that. That's what TimSort does. It looks for that kind of stuff. And it then employs 2 other sorting techniques called merge sort and insertion sort. Again, details don't matter, to try and do the sort as efficiently as possible. And also it looks nice. When you look at the graph of it running, it's somehow pleasing the way that it operates on this random set of data. And there we have the sorted list. So that's TimSort. You might like to have a look at the details if you're interested. So some things to think about in conclusion when you write an algorithm. First of all, do you really need to write your own algorithm? If you're going to be sorting some data, don't write your own sorting algorithm from scratch. We've already seen there are hundreds out there that have been figured out over the years. So use one of those. If you are writing your own algorithm, think about efficiency. Think about the use of time, the use of space. Think about how to test it. Think about how robust it is, how reliable it is, when it fails. Have you made secret assumptions that only you know about the type of data that it's going to work with? You may have thought when you designed it, I'll make it work for lists that are no bigger than 250,000. That should be enough. That'll be okay. And then somebody will use your algorithm with a list that's 250,002 elements, and your algorithm will fail. Very easy to make that kind of mistake. So that's a quick look at algorithms, which I hope will be useful for you for the future. Some resources. There's a very good book in the library, and there's some web links here. And if you only look at one of them, I suggest you look at the YouTube link for one of the Harvard courses, which talks about algorithm analysis. Okay, that's it. Thank you. Bye-bye.